We are now going to take a look at Ampere's law. The foundation for this was actually laid by Hans Christian Ørsted, who did experiments with current carrying wires brought in proximity to a magnetic compass needle. By taking a straight piece of wire and passing a current I through that and bringing the wire close to the compass needle and also changing its orientation and the distance from the compass needle, he was able to figure out that the magnetic field, that there is a magnetic field produced by the current through the wire, and furthermore that this magnetic field points in such a way that it's always threaded around the wire in a circular pattern. He was also able to figure out that the intensity of the magnetic field, that is the magnitude of the magnetic field, was proportional to the inverse distance. So the farther away you're from the wire, the distance r here, the smaller the magnetic field. It was left to Ampere to more quantitatively express how these observations can be used to calculate the magnetic field for wires of any geometry that are carrying a current. To understand that, we first state Ampere's law in a mathematical form, which is written down here. What it states is that you have to first consider a path around the current carrying conductor. The path is the path along which you are interested in calculating the magnetic field. So for example, here we have a straight conductor. This is a very simple example. And the path that we're going to consider is a circle. And therefore, we will only be able to figure out what is the magnetic field anywhere along this path if we were to use Ampere's law. And the law states that if you consider a little element delta L along that chosen path and take the magnetic field component parallel to that element delta L and multiply the two of them, so that's this part here, and do the same thing as you move along the path. So you move your delta L to different parts in the path and then consider the magnetic field at each different part which is parallel to that path at that part and sum them all up. So that's the sum, and that should be equal to some constant mu0 times the current enclosed. So in this example, the path is a circular path and the current that's enclosed inside that circular path is simply I, carried by this straight wire. Now it's important that that path be a closed path, that is true for this circular path. In the particular case that we chose, the circular path with the center of the circle on the current carrying conductor, it turns out that the magnetic field everywhere for all these little segments L is always parallel. So we can take that part out. Furthermore, since it's a circle, the magnitude of the magnetic field is the same everywhere here. So we can take that out of the summation sign and write Ampere's law in this form. And of course, when we sum the little elements delta L all along the circle, what we just get is the circumference of the circle, 2 pi r, and Ampere's law therefore becomes this form. And we can rearrange terms and express the magnetic field as B equals mu I divided by 2 pi r, where I, of course, is the current that's enclosed in the path, and that's the current through the conductor. If there are n loops instead of a single loop, it's a straightforward extension to see that you would get a magnetic field which is n times the magnetic field produced by one loop, which we calculated here. We can extend this application of Amperes law to more complicated situations. For example, if we consider a solenoid which has many turns, and we want to know what is the magnetic field in the middle of the solenoid, we actually get a very compact and simple expression. So here's Amperes law stated again: delta L times B parallel summed over the particular path that we want to consider is equal to mu 0 I enclosed. So here, the path that we're going to consider is a little bit different. Again, this is a choice that we make, and the choice that we make is such that it facilitates or makes the calculation of the magnetic field easier. You can take any path that you want, but normally you would take the path that makes the calculation the simplest. So in our case, the path is given by this orange rectangle, and which has a length L and a height D. And here you're looking at the cutout of the solenoid. In other words, this is a cross section of the solenoid. So here the current, the windings are going in and out of the board, and here the current is coming out of the board, and here the current is going into the board. So the X marks tell you that the current is going into the board. So the magnetic field, of course, if you apply the right-hand rule from our previous discussion, the magnetic field is pointing in the direction to the right, as shown by the 3 arrows. The path that we have chosen now is such that this segment of the path, the magnetic field is parallel to the path. For these two segments of the path, inside the solenoid, the magnetic field is perpendicular to the path. Therefore, the segment here and the segment here do not contribute anything to this part. And outside the solenoid, we will assume that, as an approximation, that the magnetic field is completely zero. So this segment of the path does not contribute anything because the magnetic field is zero. And similarly here, for the long length outside the solenoid, the magnetic field is zero. So therefore, we can write the parallel magnetic field, which is parallel to L here, gives you this contribution, and the other 3 segments of the rectangular path all give you 0. So therefore, you can write down B times L equals I enclosed times mu 0 is simply mu 0 n times I. Now why n? Because we have n number of turns that are inside the path. So it's n turns are carrying each of them a current I. So you get the total current enclosed as n times I. And that, of course, simplifies to this final formula: B equals mu 0 little n times I, where we define little n as the number of turns per unit length of the solenoid.